So hello, everyone. I have a very relevant presentation today. It's a visual perception experiment with NARS, the MNIST digit recognition experiment. So looking at perception through reasoning, we should be very interested in vision in NARS, since NARS sensors are how it autonomously views the world through its various modality sensors. And we can sort of view vision as the high-level understanding of low-level sensory information. So looking at this image on the left, it's an array of pixels, but I see a cardinal on the branch because when I see a red bird with pointy feather on its head and the various features of this cardinal, I realize at a high level that I'm seeing a cardinal. The problem is that at the current stage of research, NARS vision perception requires a pre-processing module, like a convolutional neural network, to detect hard-coded object classes. And this is a problem because it limits NARS concepts such that they have to be decided by humans beforehand, instead of constructed on the fly by the system itself. And we know that when NARS has the high-level abstract concepts, it can use it in high-level logical reasoning, like deduction. So if a cardinal is a bird and a bird is an animal, then I know a cardinal is an animal. But these are using high-level concepts, which we at this point expect the system to already have. But what about the raw sensory data, like the pixels of this image? Can the system do logical reasoning with sensations to build these high-level concepts or object classes on its own? Because NARS can natively compute abstractions and generalizations of high-level concepts when we give it high-level concepts. So why can't it do this with sensor data? And so the research question is, can NARS make actionable predictions by natively composing high-level concepts like compounds from low-level sensation data without the need for a separate pre-processing vision module? First, we'll go over a little bit of background and then we'll go into the experiment. So in human sensation and perception, humans have over 5 sensory modalities. We know of the basic 5, vision, touch, hearing, smell, and so on. But there's actually more than that, including proprioception, which is like internal sensors of where your muscles are located in space and so on. But regardless, for every modality, there are specific neurons which detect specific physical signals from the world. So in vision, you have red and green sensory neurons, or sensory neurons that detect red and green. These are called photoreceptors. Touch, which detects things like pressure, mechanical pressure, and temperature receptors. And hearing, which detects various pitches of noises, so high pitch and low pitch. And what's interesting is that in animals and in humans, these sensory neurons connect to the brain in a special way that preserves their spatial layout. And this is called a topographic mapping. And this is pretty easy to imagine or visualize in the vision modality, just because images are very spatial in nature. But this topographic mapping actually occurs for most, if not all, sensory modalities. And that includes things like touch. So if you see this picture on the left, this is a somatotopic or touch map. And basically what it means is that neurons which are nearby in physical space will be nearby in the sensory map. So the head neurons are connected to the shoulder neurons, which are connected to the arm neurons, or nearby in a topographic map. And the same thing with hearing. Lower frequencies are closer to neurons which detect lower frequencies are closer to neurons which detect similar frequencies, whereas on the other end of the spectrum, you have neurons detecting like high frequencies. And so sensory neurons can be activated strongly or weakly or not at all, depending on the stimulus. And this forms a unique 2D stimulus pattern on the topographic map. And so these patterns of sensation that the system is receiving all the time, this is the system's inputs, or in our case, the brain's inputs. So the brain is using topographic or spatial maps to understand the spatial layout of its sensations. And if NARS is analogous to the brain, then the question is, can we modify NARS to accept sensory topographic maps as well, and then test NARS performance? And that's essentially what this experiment is all about. So about the test itself, the MNIST digit recognition test is a famous test for computer vision. Goes back a couple of decades. And the idea is that the computer system will succeed at the test by correctly identifying the digit that is shown in the image. So here on the right, this is an example from the MNIST dataset of digit 3. And the dataset consists of thousands of labeled images of handwritten digits between 0 and 9. And these images are 28 pixels by 28 pixels. This is 784 pixels, total pixels per image. And each pixel is represented by an intensity value in the range 0 to 255, where 0 is completely black and 255 is completely white. And then in between are your grayscale values. And this is a pretty decent test for NARS perception because we can treat each image like a topographic map, a visual topographic map or retinotopic map of 784 low-level sensory photoreceptor activations, from which NARS could ideally infer the high-level object class, which would be the digits label. And so to use an image in NARS, we could treat each of these pixels in the image as a specific instance of a vision sensor, like each pixel would represent like a single photoreceptor. And then each instance of a sensor inherits a certain property, which is whatever that sensor detects. So it might detect intensity values or brightness values, redness, like in humans, greenness, blueness. But it can even detect any other feature, things like vertical edges or edge orientation, like edges that are at 30 degrees or 60 degrees or various orientations of edges, or really any feature that you desire. But here we just use the brightness property to indicate the individual pixel's brightness or intensity. And then what we do is we encode each sensor's activation as an atomic NARS event, where the frequency is the intensity of the sensation. So a pixel with no activation would have 0 frequency, and a pixel that it's at full activation would have a frequency of 1. And then we encode the confidence as just a unit amount of evidence. So like one piece of evidence, essentially. And an example of this, you can see in this image, we have a bright pixel over here, and it's encoded as this event where the arrow is pointing. So this pixel at location 14.6 in the image is bright, and let's say it has 0.95 intensity, 0.95, that's a normalized intensity. And so the change to the NARS architecture that you have to make is to store the events in a 2D buffer or spatial buffer that retains the spatial layout of the sensory events. And this allows the system to group the various sensations or sensor events by location. And then also store a reference to every event in a bag, standard NARS bag, using the event's truth expectation as its priority so that events can be randomly selected with a certain probability. So the way it works is, first, NARS probabilistically selects one of these events from the bag, and then it uses this as a pivot event. And then, since spatially nearby events are more likely to be related to each other than spatially distant events, so this event here at the top of the 3 is quite unrelated to these activations here at the bottom, NARS can group the events using a spatial window around the pivot. And in psychology, this is actually an established theory or model of attention. This is called the spotlight or zoom lens model of attention. And there is further reading on this. And so in NARS, multiple events that are selected in the window are then combined into a single compound event using the conjunction or composition. So if the window selected 2 events, it would create a compound like this, where the 2 atomic events are combined using conjunction. And this statement is actually, this is a higher order statement, but it's actually equivalent to the first order intentional intersection of the events. And so that's what this is down here. And so if you look on this image here to the right, this is an example of having the spotlight of attention on the topographic map. This is a 5x5 attention window. And so a window like this would compose up to 25 events into a single compound. So in this experiment, we were interested in two different tests: memorization, which is can NARS remember images that it's already seen and recall them in the future, and also recognition. And this is can NARS label new images that it's never seen before, based on, say, some training set of images. And so the setup was to divide, it's a very traditional setup, where each experimental trial is divided into the training phase and the testing phase. So first, the system is shown labeled images, and this is in the training phase. So it's shown an image and then told a label for the image, and it can temporally associate them. And then the knowledge is tested in the testing phase. So in the training phase, NARS is allowed to just observe the training image for some set number of cycles, and then input with a label, which is another event, which informs NARS which digit that it's currently looking at. And so for an example of a label would be, you're looking at the digit 5, or this digit 5 is seen. And then during this phase, NARS temporally associates visual features with the digit label event using temporal induction. So if NARS might make a statement like, if this pixel is bright at this specific location, if this photoreceptor is activated essentially, then I'm looking at the digit 5. And then whenever NARS sees that event again, it can predict what it's looking at. So it will predict that I'm seeing digit 5 whenever it sees that this specific pixel is activated. And then in the testing phase, NARS is given seed goals to execute a specific operation for a digit if that digit is seen. So for example, the goal might be, if you're seeing the digit 5, then press the digit 5 button. And goals are input into the system for all 10 digits. And so therefore, when NARS predicts certain events, like I'm seeing these visual features, so I'm predicting I'm seeing the digit 5, NARS can then use deduction to derive evidence for the operation goal, like to press the digit 5 button, which will then cause it to execute that operation if it exceeds the decision-making threshold. And so the success criteria is whether NARS predicts the correct digit or not, executes the correct operation or not. And so NARS gets one chance to answer for every image in the test set, and it answers by executing an operation. And then depending on what operation it executes, the answer is recorded as correct or incorrect. And there's also a timeout because NARS is not guaranteed to give an output. It can give an output or it cannot if no operations exceed the decision-making threshold. And so there is a timeout of 3,000 working cycles in this experiment, where if the system does not recognize any image features or the labels, then it might not execute any operation at all. And at a certain point, we have to cut the system off and say, okay, you're not going to get this digit. You got this one wrong. So the basic idea is that NARS will scan the image continuously and compose visual features into compounds. Then NARS continuously makes predictions of the image class based on the compound features that it's seeing. And if enough evidence for various predictions accumulates in that memory, then NARS will use them in goal inference. And so the hypothesis is that NARS will predict certain digits correctly with high confidence. And by grouping multiple events, the compound event will be specific enough to predict the digit class, but generic enough to recognize variations on that digit. So images that NARS has never seen before. This is compared to like a single pixel, which would be far too generic because many different types of images, many types of digits might activate one pixel. But also NARS can't just store the entire image in its memory. That's far too specific, and it's very unlikely that another image of that exact same layout will be seen again. So it needs to do something sort of in the middle. And here's a video of the experiment. And so the image on the left is the image that's being presented to NARS. And the image on the right is what NARS is currently paying attention to and at the current working cycle. And so you'll notice that it sort of jumps around and compounds, composes features from different parts of the image. And so this is the training phase. It's given 125 working cycles per image. and it's shown 300 training images. And so here at this point, it's essentially composing visual features into compounds and then temporally associating them with the labels. Here, the label is being given because this is the training phase. Then in the testing phase, NARS does the same thing. It composes the various visual features, but at the same time, it's continuously making predictions based on the implication statements in its memory. And so here you can see that actually, in many cases, NARS is predicting the correct label for the digit. So here the system was looking at this digit 3 and it viewed various features, and then it predicted that I'm seeing the digit 3. And if you watch this video, you'll see certain situations where the system sort of gets tricked into predicting the wrong digit because the windows that it's looking at, these small windows it's looking at, are sort of ambiguous. So like a 3 might sort of look like an 8, depending on the small window it's looking at. And so here's the overall results for the 4 tests that were run. There was a memorization of digits 0 and 1, a memorization of digits between 0 and 9, classification of novel images for binary digits, and also classification of digits between 0 and 9. And so what you'll notice is that NARS performed both the binary and the digit memorization perfectly with 100% accuracy. And it could classify new images of binary digits or the digits 0 and 1 about 98% of the time correctly. But the most impressive was the hardest test, which was the digit classification, which is identifying digits of 0 to 9 that it has never seen before. And in a single trial out of 100 images, NARS was correctly able to classify 50% or 50 of the images, approximately. And this is much better than the random chance we would expect if NARS was, well, NARS is not actually guaranteed to output any operation, but if it was, we would expect random chance to give an accuracy of about 10% if NARS was randomly guessing. So this is pretty statistically significant. NARS is classifying almost 50% of these images correctly. And it's doing this simply using composition, induction, and deduction rules. So just simple inference rules with no pre-processing involved. And there's also the personality parameters for various tests. Here in the most impressive test, the decay rate for events and goals confidence was 0.95. The evidential horizon was very standard, k equals 1. And the decision-making threshold was fairly moderate at 0.65. And so analyzing these results, we can see that the spatial grouping of visual features for compositional inference actually allowed NARS to predict correctly the class of novel images. And interestingly, the system achieved higher accuracies when modified to use static sized attention windows rather than allowing the window to randomly change in size randomly. But this also limits the system in that it can only look through specific size windows of the image as opposed to more adaptive size windows. And so in the future, the attention window should change according to some factors. The system also performed better when given access to select disjunction of events. This is like a form of max pooling, which provides robustness to small local translations of digits in the image. So if you have this 4x4 feature map, it might be these features might be too specifically located for NARS to recognize it. So you can actually use disjunction to sort of fuzzy the image up such that like features, if the features are slightly translated to the left or to the right or down or up, when you pool them using disjunction or operator, NARS is more likely to recognize them. And just looking at the limitations of this and possibly future directions, one problem was that the system couldn't choose its own attention window. It was randomly sized or in fixed size. And so it would especially be useful if NARS could use its own top-down predictions to better analyze the stimulus. So like if NARS sees the color red, it might predict that it's going to see a cardinal, and so it will additionally look for beak features to confirm. Also, NARS only had a pixel intensity map. Humans have neurons in visual cortex V1, which detects specific edge orientations like vertical orientation of edges or horizontal, and the various degrees in between across the entire visual field. And you could also represent these as an activation map. Related question to this is, do these edge orientations, for example, need to be detected with a pre-processing algorithm, or can NARS do this natively? So could NARS, for example, detect vertical edges using Boolean operators? This is a question. And the explicit kind of spatial window used here might be sort of a naive approach versus maybe a more implicit and parallel spatial composition, which you could achieve with neural networks. But still, these results pretty much show that the promise of spatial grouping and evidence-based reasoning, it works for sensory understanding. And here NARS was trained and tested in passive image classification tasks, but future tests could take place in a more active context by testing NARS in a real-time interactive environment. These are my references. And that's all. Thank you.